All right, for our next videos, we're going to be looking at quadratic functions. So first off, what is the standard form of a quadratic function? What is the basic quadratic function, or what are all quadratic functions kind of getting at? It's anytime you can write a function in this form. F of x, which remember we could also call y if you wanted. So I'm just going to draw a y over it. Y equals ax squared plus bx plus c. You'll notice there's a c that is alone. That's our constant piece. There is a bx. This is called our linear term. Constant term, linear term, because if we didn't have this over here, bx plus c, that is a linear equation. All we're doing is adding on to this linear equation this piece, our quadratic term, the ax squared. Now I want you to make sure that you have in your notes a certain spot set aside just for all of the vocab here. And your first vocab that I want, put a little star by it, this standard form, you can either call it y or f of x equals ax squared plus bx plus c. This is the regular form of quadratic functions. Now, comparing linear and quadratic, remember that linear functions have a constant rate of change. So you're always changing by the same amount. So we were talking before about maybe people running. Maybe Bill and Joe are both running, and they both run at a certain speed. Well, they constantly run at that same speed, and that's what makes kind of that line on the graph. If we have our quadrant here, this line going this way constantly, this line going this way, and they catch up. So it's a straight line because their rate of change is always the same. Now that's not true for quadratic functions. The rate of change itself is changing, basically saying people are getting faster as they're going or slower as they're going over time. So you don't stay going that 60 miles an hour or $5 per week or whatever it is. Your rate changes is what we're getting at. So I want to look at a table comparing certain things. So again, my input, my domain is x. So here are some input values like -3, -2, -1, and so on. When I plug it into all of these different functions, these are going to be my outputs. So if I plug it into a linear function, just a simple y equals x, I get out the exact thing that I put in. If I plug it into an absolute value kind of a function, notice they almost look the exact same, except for these are not negative. These ones are positive values. That's why the absolute value looks so much like the linear function, because everything looks almost the exact same, except there is a certain turnaround point. That's why it makes a V and not a straight line. When we use the quadratic function, though, this is where things kind of get doubly interesting. They change in more than one way. So no longer do we have these negatives. Just like the absolute value, a quadratic will have everything as positive. So quadratics and absolute values are similar in that there's that turnaround point. This area, this 0, 0, is the vertex. It's kind of the middle or the turnaround point for both the absolute value and the quadratic. So that's how these two are similar. The quadratic is different from these other two, though, because you'll notice it's not changing by the same amount each time. As we go from changing x from 0 to 1 and 1 to 2 and 2 to 3, we're always changing by 1. And so your function is again also always changing by 1. Just like this one, from 3 to 2 is 1 down, 1 down, 1 down, all of a sudden 1 up, 1 up, 1 up. It's always changing by 1, just like these are always changing by 1. These ones are not always changing by 1. From 9 to 4, we're going down 5, then down 3, then down 1, then up 1, then up 3, then up 5, then up 7. So you'll notice that changing amount, or the amount that we are differing by each time, changes. With the absolute value, it's always the same. You're always changing by 1, either up or down. With the linear, you're always going up 1. This one, you're not always going up by the same amount. So that is how the quadratic function is different than the linear function. Now, if we were to double everything in our linear function, notice all I did was just take all of these and double them. So again, I'm going up by 2's here. So -6 to -4, I'm adding 2, add 2, add 2, add 2, add 2, and so on. Well, notice how big of an effect it has for our quadratic. I'm starting at 18, I'm going down 10, down 6, down 2, up 6, up 10, and so on, up 14. So you can notice and see how the quadratic function, the rate of change changes so drastically and so quickly compared to linear and absolute value functions. You don't need to write this down. I just wanted to show you this is what's going on with our quadratics. This is how quickly or how fast they get big. So again, let's just see what that would look like if we were to plot it out. So if we were to take our x values and plug them into this function, y equals x squared, if we had a -4 is being squared, -4 times -4 is 16. -3 times -3 is 9. -2 times -2 is 4. -1 times -1 is 1. Then 0. Then 1. Then 2. Oops. Sorry, that wouldn't be 2. That would actually be 4. So 1, 4, 9, and 16. So again, all I did was plug in my x values into the function. Now, looking at this table, I can graph this. So here's a spot at 0, 0. Here's a spot at 1, 1. Took care of this one, took care of this one. There's also a spot at -1, 1. So that one gets taken care of. There's a spot at 2, 4. There's also a spot at -2, 4. So those two. There's a spot at 3, 9. There's also a spot at -3, 9. So I can take care of those two. You'll notice how quickly these go off the chart. These will all of a sudden be way up here at 16, up where I can't even get on my chart. So look how quickly this curves upward. So it is not a straight line, it is curved, and it curves on both sides. Kind of makes this U shape. It's not necessarily a V. It does come to this point, but it curves throughout. So we always are thinking about from the vertex. Just like over here, we can see we started at the vertex and everything curved out. Just like when we had our absolute values, we always want to define the vertex and then slope out from there. With quadratics, we want to work from the vertex. So if we think about our vertex being here, when the x changes 1, then the y changes 1 as well. To view that visually, I can go from here, I'm going over 1, up 1. So as x changes 1, y changes 1. As x changes 2, my y is actually changing. Oops, wrong direction. So as I come 2 over, my y is actually going up 4. Oops, too much again. So as my x goes over 3, my y is actually changing by 9. When my x goes over 4, my y is actually going up by 16. And when my x goes over 5, my y is actually going up by 25. And lastly, 6 would be a 36. So I could plot my points as though I was coming from the origin, like this. However, I want you to think about the fact that this vertex can move. Even if the vertex moves and say it's way down here, we are still moving over 1, up 1 on both sides. So as x changes 1, y goes up 1. From the vertex over 2, up 1, 2, 3, 4. over 2, up 4. So this parabola, this curve, is starting to look the same as what it would be here. All we did was move the vertex over. Again, from this vertex, I'm going to go over 3, but up 1, 2, 3, 4, 5, 6, 7, 8, 9. So there and there. Again, all I'm doing is thinking about my changes, but from the perspective of the vertex. From the vertex here, over 1, up 1. Over 2, up 4. Over 3, up 9. If I wanted to go again, I'd go over 4, up 16, and so on. And this would help me graph my parabola. I just have to think about where my vertex is at and how it is moving. Now, as we draw the parabolas, you can see that the parabolas are symmetrical. They have what's known as reflection symmetry, since there's a line of symmetry that divides the curve exactly in half. So if I were to draw in this parabola, there would be a mirror line that cuts it in half. So this mirror line we call the axis of symmetry. So it goes right here, and you can see that this whole parabola is mirrored away from it. This dot is 3 away, this dot is 3 away, this dot is 2 away, this dot is 2 away, this dot is 1 away, this dot is 1 away. And of course the vertex is right on. So this mirror line is called our axis of symmetry. I want you to put this down in your vocab. The axis of symmetry goes through the vertex. So the equation for the axis of symmetry is x equals negative b over 2a. This negative b over 2a comes from our vertex. I want you to pause now and try to find the vertex, the axis of symmetry, and the y-intercept on your own of each of these, and then we'll try it on together. I'm going to assume that you paused and were able to figure this out on your own, so let's double check. For this one, we can see our vertex is here at negative 1, negative 4. That would mean then that the mirror line, this axis of symmetry, is on the line x equals negative 1. We'll use the x value of the vertex. The y-intercept is where it crosses this y-axis. That happens right here at negative 3. For this one, we're going to do the same thing. Here is our vertex, where everything else is stemming from. That's at the point negative 1, 1, which means our mirror line, this axis of symmetry, is the line x equals negative 1. And we can see then y-intercept, it crosses this y-axis at positive 2. Notice these both have the same axis of symmetry. We just moved the vertex up some. So this one was way down here. We moved it up to this point to make it look like this one. I want you to pause again and see if you can figure out the vertex, axis of symmetry, and y-intercept of these ones. I'm going to assume that you pause and figure these out. So we're going to try this together. Here again, we find our vertex, the place where everything's stemming from, at 2, negative 1. That means the axis of symmetry is the line x equals 2. It's the x value of our vertex. And lastly, you can see that it goes through the y-axis here at 3. So our y-intercept is 3. For this last one, we can see it stems from the origin. So our vertex is 0, 0, which means the mirror line, our axis of symmetry, is the line x equals 0. And if our vertex goes through the y-intercept, or the y-axis, then our vertex is on the y-intercept. So our y-intercept in this case is 0. I want you to do the same thing, but with these equations. So again, to find the vertex, you're going to use that negative b over 2a for these pieces. Once you do that, that'll be your x value. Plug the x value back in and solve. That'll give you your y value. That will tell you the vertex. Once you know the vertex, the axis of symmetry is just the x value. X equals the x value of your vertex. And remember that the y-intercept is always where your function has an x equals 0, because you're right on the y-line. So you can plug in x is 0 and solve for your y-intercept. I'm going to have you pause now and try that on your own. I'm going to assume that you tried those on your own. Let's try those together to see what we get. Using negative b over 2a, I'm going to write my work right here. Negative b, so negative 4, over 2 times this a value is 1. 2 times 1 is 2. Negative 4 over negative 2 is negative 2. So that's my x value of the vertex. I can go ahead and just write x equals negative 2 as my line of symmetry, or my axis of symmetry. Now that I know negative 2 is the x value of my vertex, I can plug it back in here and solve for my y value. Negative 2 squared is negative 2 times negative 2, which would come out to 4. 4 times negative 2 is negative 8, so 4 plus negative 8 plus 12. 4 plus negative 8 is negative 4. Negative 4 plus 12 is 8. So my vertex is at negative 2, 8, and my line of symmetry is at x equals negative 2. If I plug in zeros here and here, these pieces will cancel out, and I will only have 12 left. So my y-intercept is simply 12. If you haven't caught on now, the trick is your y-intercept is always just this last piece. If this is given in standard form, this last piece is your y-intercept. So let's see what happens on this one. We're going to do the same thing. Negative b, so I'm actually going to put in a positive 8 because it was a negative 8, over 2 times 1 is 2. So positive 8 over 2 is 4. So 4 is the x value of my vertex. I also say x equals 4 is my axis of symmetry. Plug that 4 back in. 4 squared is 16. 8 times 4 is 32. 16 minus 32 is negative 16. Negative 16 plus 10 is going to be negative 6. So my vertex is 4, negative 6. My axis of symmetry is 4. And remember, this last piece, this 10, is always going to be my y-intercept. Well, it looks like my GIF didn't really turn off. I'm just going to leave that there. I want you to, again, pause the video and try finding the vertex, axis of symmetry, and y-intercept of these two functions. I'm going to assume that you paused the video and did these on your own, so let's check these. In this case, notice that there's only the two terms, quadratic and linear. There's no constant term. If that freaks you out too bad, I want you to just add in the plus 0 at the end. That way you can see there's still the three terms. My a is 1, my b is negative 6, and my c is 0. Now I can go ahead and still do negative b over 2 times 1 is 2. 6 over 2 is 3. So my x value of the vertex is 3. Axis of symmetry is x equals 3. I plug in my 3 back into the equation. 3 squared is 9. 6 times 3 is 18. 9 minus 18 is negative 9. My vertex is at the point 3, negative 9. My axis of symmetry is x equals 3. And again, with this 0 here, my y-intercept is at 0. Now we're going to look at the other one. Again, x squared and plus 7. We have our quadratic term, we have our constant term, we are missing the linear term. If that freaks you out too much, again, you can just go 0x as your linear term plus 7. This expression is the same as this. All I did was add in this 0x. Now, it makes things a little bit easier to see that negative b over 2a would be negative 0 over 2. 0 divided by anything is 0. So my axis of symmetry is x equals 0. My x value of the vertex is 0. Plug 0 back in here. 0 squared is 0 plus 7 is 7. And here's my y-intercept of 7. That'll end our first video. We've discussed standard form of quadratic functions, how parabolas look, the vertex of a parabola, the axis of symmetry of a parabola, and the y-intercept. We've also discussed how to find all of these in our standard form.